This video covers reporting category 5, which is notes 17-7. So this is the last reporting category before we take our 3-day test. So part 1 is about graphing exponential functions. Exponential functions are written in the form f of x equals a parentheses b close parentheses to the x, where a is the starting amount and b is the percent change. A is always the y-intercept or starting rate, and B is the growth rate. We've listed on the right side some other reminders for words you could use for A. A is your y-intercept. It's your initial value, your starting amount, your starting value, your starting point, etc. B is the base of an exponent in an exponential function. That's why they use B for base. If B is greater than 1, the function is increasing, and we call this exponential growth. As you read this graph from left to right, as it's shown on the bottom, your x's are increasing and your y's are increasing. Overall, if you follow this across, your x's are going up from here. If b is between 0 and 1, for example, a small fraction or a decimal, the function is decreasing, and we call this exponential decay. The graph, as we read from left to right, my y's are decreasing. So exponential decay is something that's fun to ride on as a skateboarder or a bicycler or anybody that's a thrill seeker, and exponential growth is not a fun thing to drive your bike up. The asymptote is a line in which a function gets close to but never ever touches. An asymptote is kind of like a wall. If there's a wall here, a person can go all the way up to the wall, be right on top of the wall, but unless there's a hole cut out in the wall, you can't ever be in the wall. So an asymptote is kind of like a wall. It's a space where you can get really, really close to. You can be right up on top of that wall, but you can't ever be exactly where the wall is, because if you're where the wall isn't there anymore. So an asymptote is like a wall. Our function runs into the wall and can't be there anymore. So using the information, answer the following questions. So we have a graph here. We can see as we read from left to right, our graph is decreasing. So our x's are increasing, but our y's are decreasing. So let's answer some questions. The asymptote for this function, let's start at the graph since I started there. This graph is decreasing. My x-intercept starts at 1, so we start or cross at 0, 1. My domain for all exponentials is all real numbers. My asymptote and range are directly related. We can see here that this is getting very, very, very close to this line, but this is where my wall is. So my wall is a horizontal line. So hoi, so I need a y equals, and it's when y equals 0 that we run into problems. Therefore, my range is everything greater than 0, but my range cannot equal 0, so I do not put a line under the inequality. This one, because it is decreasing, would signify exponential decay, because my graph goes down from left to right. Using the equation, my asymptote here is going to be at y equals 0 because there's no changes that are happening, and most of the ones that we see are at y equals 0. If you're not sure, you can plug this equation exactly like you see it into y equals. Remember to go up to do the exponent. We use the up caret to plug in an x, and I can see my graph, and my graph hits a wall here at 0. So my asymptote is at y equals 0. My y-intercept is going to be 0, 2, because that first number is my y-intercept. Domain, just like the other one, and all exponentials, all quadratics, all linears, are all real numbers. And my range is everything greater than 0, not equal to. Because my b value is bigger than 1, it is growing, so this would show an exponential growth. So if we are asked to write exponential functions, there's a couple of things we have to remember. This formula is not on our formula chart. So you have to remember it starts, 1's your base. To grow, you add the rate, and then raise it to the exponent. It's not that much different than our actual exponential function. So let's get started. So the population of a city is increasing at an annual rate of 4.5%. When the increase began, the population was 1,800. So our A value, our starting value, our y-intercept, our starting point is 1,800. The meaning is that we start with 1,800 people. Our R is 4.5%. So with percents or with decimals, we Beyonce them to the left, to the left. So my R is 0.045. So my growth factor is going to be a total of 1.045% because we take that 1 and add our rate for our new base. And because it's bigger than 1, it means that we are growing. Okay, so remember, all of our percents get turned into decimals. Our b value is really 1 plus our rate because we're growing, so we add to 1. So it's 100 plus our percent. So our equation is going to be 1,800. Our rate is 1.045. And this is raised to the x. Now, to make any predictions, I'm going to plug this into y equals. So 1,800 times 1.045 raised to the x. Okay, and for predictions, you most likely are going to need the table. So they're telling me, or I'm using y. Y is my population, so years is my x. So for 5 years, the population would be 2,243 people. We round, but we do not use decimals because we can't decimal people. We can't have part of a person. And then in 10 years, x would be 10. So my population would be 2,795 people. So again, I took my equation and I put it into y equals and used the table to find my missing pieces. In the middle, we're given exponential decay. The only difference between growth and decay is the sign and what you do with 1. So we're talking about a new van. It sells for $25,600 and it depreciates at a rate of 15% each year. So my A value, my starting value, is 25,600. It means we start at that value. My rate of decay is 15%. Remember, we turn it into the decimal by Beyonceing it to the left, to the left. So my decay factor will be 1 minus 0.05, which is 0.85. If you don't believe me, plug it into the calculator. 1 minus 0.15 is 0.85. And this means that it is decaying. So in my equation, I have the starting value already. This is what we start at. And then because it's less than 1, my rate needs to be something less than 1 to show decay. So in y equals, I'm going to plug my equation in. 25,600 times 0.85 raised to the x. So in my table, again, years is still y's. So in 3 years, it's going to be $15,721.60. And this one, money rounds to 2 numbers after the decimal. And then in 5 years, it's going to be worth $11,358.86. And we again round that to 2 decimals because of money. Now, if you're given a table which tells us it's the value of a mountain bike versus the year since it was purchased, we are going to put that in stat calc. So 0, 1, 2, 3, 1,200, 1,080, 972, 874.80. Okay, and because we're talking about exponential regressions, we're going to scroll all the way to 0. So A is 1,200, meaning we start at $1,200, which we can see from the table. And then B is 0.9, meaning it is a decaying value. My equation, remember they show us up at the top, it's A times B raised to the X. So A is 1,200 times B, which is 0.9, raised to the X. On this graph, we are just asked for our A value. Our A value is 10. So this means we start with 10 Y's. My Y's is bacteria. So we start with 10 bacteria. Is it bacteria? Is bacteria? I don't really know. But remember, A is where it crosses the y-axis. So if you're given a graph, just look for your y-intercept. And then we're going to finish up with a couple last things. Regressions with scatter plots. This is not necessarily this is not necessarily exponential. Anytime you see the word regression, it means stat calc. So in these examples, we do not know what it is, so we have to look at it. So in this first example, they ask us to identify which function best describes each of the following. So we know with regressions, they don't make a nice pretty line, so we just kind of draw some lines in between them. This one looks like an upside down U, and that U reminds us that it's quadratic. So this would be a quadratic function. This one we can see there is a straight line going through it. Straight lines are linear or linear. So lines for linear. And then for the last one, we can see a line as well. It is not a straight line. It looks like Buzz Lightyear, where it goes up into infinity and beyond and never comes back. So remember with StatCalc, 4, 5, and 0 are the options that we try if we're ever given a table and no ideas. So, based on the answer choices given in this 2015 EOC question, which type of regression would you use for this problem? So they give us a table. All of our answers have x in the exponent, which makes it an exponential function. So, by looking at the exponents, or by looking at the answer choices, we know that we can ignore options 4 and 5 and just run one thing in StatCalc. So in my table, x is 0, 1, 2, and 3. I already have that, so I'm just going to replace here 0.0625, 0.25, 1, and 4. Remember that we press enter behind each entry. And again, we've just looked and said that all of my answers are in 0 expreg, so there's no point in running linear or quadratic. And when I do this, I get that my starting value is 0.0625. H is the only answer that has 0.0625 at the beginning. If I had more than one, then I would also need to make sure that this is correct. But again, sometimes you can just get to the answer by looking at one tiny piece. A couple of quick reviews on vocab. An asymptote is an imaginary line that a curve approaches but does not meet. All of the ones that we've looked at are horizontal, but you can have vertical ones as well. Your y-intercept is the point where the line crosses the y-axis, so it's always the point 0, number. Exponential decay, the b value is between 0 and 1, and y is decreasing. Exponential growth, b is greater than 1, and y is increasing. Rate of change is how much y changes compared to x, so as x increases, y decreases, or as x increases, y increases. A conclusion is a judgment or decision reached by reasoning.